Hello class, welcome to today's lesson. We're going to be proving and applying similar triangles. In other words, using our concepts about similar shapes with triangles. Your examples and pre-learning for this exercise are example 8, using similarity tests to prove similar triangles. And your pre-learning for this example is questions 1 and 2 in the new book and question 4 in the old book. And then we'll be doing example 9, which is establishing and using similarity. And your pre-learning for this will be questions 5 in the new book and question 7 in the old book. Later in this unit, we're going to learn more about trigonometry than you have in previous years. This concept of similar triangles is essential for trigonometry. In this lesson, take care to not just go through the motions, but actually understand all the rules, the tests, and the properties we learn, as well as the concept as a whole. Doing this will make trigonometry very easy for you. And if you stick around to the end, you'll be glad to know that challenges have returned. Okay, we'll see you in introduction. If we have two triangles, ABC and DEF, with side lengths ABC and side lengths DEF, if they are similar triangles, then by definition, all angles are the same. All side lengths for ABC have a corresponding side length in DEF with the same scaling factor. And corresponding side lengths are in the same ratio to each other. So to test if ABC is similar to DEF, we can test if all angles are the same. For example, these two triangles have angles 30, 70 and 80. And I'm going to write the names of the tests on the side here. So this first test is AAA, which means angle, angle, angle. We could also test if all sides in one triangle are in ratio to a corresponding side in the other triangle. So for example, this triangle has sides 2, 4 and 4, and by a scale factor of 2, this other triangle has sides 4, 8 and 8. And the name of this test is side, 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 or SSS. It's worth pointing out that the first two tests here are really just definitions of similarity. We can also test if two pairs of sides are in the same ratio and the corresponding angle is the same. So for example, these triangles here that have sides 3 and 4 with 40 degrees and 4.5 and 6 with 40 degrees are similar because 4.5 equals 1.5 times 3 and 6 is equal to 1.5 times 4. Or 4.5 on 6 is equal to 9 on 12 when I multiply top and bottom by 2, which simplifies down to 3/4. So therefore you can see we have the ratios between the sides that matter. And obviously they share the same angle, 40 degrees. And this type of test is called side, angle, side, or SAS. Now you can just believe me on this, or showing why it's true will be a mini challenge. So if I was to construct a triangle like this, then drawing a parallel line to this bottom one, extending these two side lengths, you might be able to show why it's true by using what we know about distances between points and parallel lines. But I'll give you more detail of the challenge at the end of the lesson. And the final test we have is to see if the hypotenuse and one other side of a right angle triangle are in ratio to each other. So for example, a right angle triangle with a hypotenuse of 2 and one side of 5, and a triangle with a hypotenuse of 7.5 and the same corresponding side to be 3 are clearly in ratio to each other because 7.5 divided by 3 is equal to 15 on 6, which is equal to 5 on 2. So this shows that they're similar. The name of this test is right angle hypotenuse side, or RHS. Hopefully you can see that this is basically the same as side angle side, but also very important for trigonometry. Either way, let's check these out in GeoGebra by following this link. Just like the quadrilaterals in our last lesson, we can create a similar triangle as the one created by these points by just moving this slider here. Now let's quickly demonstrate some tests for similarity in triangles. First, let's move this point around here so that we can notice that no matter what angles are, they are the same in both triangles. So here you can see we got one angle of 86, another one of 36, another one of 56, and some decimal places. And if I move it over here, we can see that our angles are now 31, 71, and 77. And looking at the bottom lines, we can see that the original triangle has a side length of 6. If I make the slider 2, then we'll see that the other one has a length of 12. We can also see that 3.16 times 2 is 6.32, and 5.83 is equal to 11.66. So we've now shown that all the angles stay the same and all the sides have the same ratio. Now let's move this triangle into a right angle triangle. Now leaving the slider at 2, we can see that the hypotenuse is 5 in one and 10 in the other. And the side on the left is 6 in one and 3 in the other. And clearly 6 divided by 10 is equal to 3 divided by 5. Hopefully you recognize how important this is for trigonometry. Okay, so for example, the sine of 36.87 degrees is equal to 5 on 3 or 10 on 6. So staying with this right angle triangle, you can see that by extending our left hand side to 6 and our right hand side from 5 to 10, we've increased our sides by the same ratio, and our angle of 53.1 degrees stays the same. The only side that connects all the way across the bottom for the hypotenuse of size 10 is 2 times 4, which is 8. Though you might not be convinced we're only looking at a right angle triangle, let's look at all triangles by drawing this line that goes from the 90-degree angle through to the midpoints by clicking this checkpoint here. And if I drag this point around now, you can see that the line from that angle to the midpoint of the opposite lines is always a straight line. So perhaps this gives you a clue that you can prove the SAS rule by using similar triangles of smaller triangles inside your big triangle. Anyhow, let's go back to the OneNote. Okay, back in the OneNote now, it might be a good idea to try building understanding questions in the new book, which translates to questions 1, 2, and 3 in the old book. Okay, I'll see you in the next section. In this section, we're going to use the similarity tests, AAA by checking if all the angles are the same, SSS by checking if the ratio between all the corresponding sides is the same, SAS by checking if there are 2 corresponding sides with the same ratio and a corresponding angle. And finally, right angle hypotenuse side by checking if it is a right angle triangle with the hypotenuse and one other side in ratio. Okay, so let's put these tests to the test in example 8, where we'll prove the following pairs of triangles are similar. In part A, we have this triangle ABC, and the side AB is 1.5, and the side AC is 2, and there is an angle 20 degrees between these two sides. And the other triangle is DEF, and that has a side of 3 and 4 with the angle also 20 degrees. We can see that both angles, BAC and EDF, are 20 degrees. So we can look for scaling factor, but we can just look at the ratio between these two sides. So DE over DF is equal to 3/4, and AB over AC is equal to 1.5 over 2, and multiplying top and bottom by 2 equals 3/4. So both triangles have sides that are in ratio with each other and a corresponding angle that is equal. So by SAS, ABC is similar to DEF. All right, let's have a look at part B, where our triangle ABC has angles 40 degrees and 65 degrees. And I should mark in the points A, B, and C. And we have this other triangle over here, DEF, that also has the angles 65 and 40. So here we can see both triangles have an angle of 40 degrees and another of 65. So by the angle sum, the other angle must be 180 minus 40 plus 65, which is equal to 75 degrees. And I'll mark them in here. So now we've got two triangles with all three angles the same. So by AAA, angle, 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 ABC is similar to DEF. Okay, so that's an example of 2 tests. Pause the video now so you can work on questions 1 and 2 in the new book or questions 4 and 5 in the old book. But seeing we've only tried out 2 tests, make sure that you do at least 1 question for each test. Alright, I'm going to see you in the next section. In this section, we use the 4 tests for similarity. Then when we know the triangles are similar, we can also know other properties of a triangle. Alright, let's get straight into example 9. Here in example 9, we've got a picture of a cone like so. Now the height of this cone is 4 centimeters. And we'll mark this as point B, which starts in the very middle of the bottom of the cone. And the top is A. And the radius of the circle at the bottom is this line from B to C. And it's 2 centimeters long. And this is the definition of a cone. Its radius to mark out the circle on the bottom and its height. And if you looked at this slant side of the cone and the line AB and the radius BC, then this triangle defines our cone. If we were to make a perfect cut on the height of D to E, we might be able to figure out some things with similar triangles. But before we go on with that, let's have a look at this thing in GeoGebra. And you can follow this link here. You can see this exact cone in the 3D version of GeoGebra. If I hide this cone, you'll be able to see the triangle that defines the cone. And if I slide D up and down, this straight line it makes to E is exactly what our horizontal cut would be. And if I just rotate this triangle around, you'll be able to see what this triangle looks like. Now let's turn this cone back on and get back to OneNote. So after looking at the GeoGebra applet there, you could see that I could represent the triangle in the middle as these points A, B, C, D, and E in a 2D triangle. Right, in part A of example 9 here, we're asked to prove that ABC is similar to ADE. Now it should be obvious to you that all the angles are the same because BAC is DAE. And ADE and ABC are both right angles. Also, AED and ACB are corresponding angles. So by AAA, ABC is similar to ADE. Okay, so now we know that they're similar. Part B is asking us, if AD was equal to 1 centimeter, find the radius DE. So let me redraw that triangle, marking AD equal to 1 centimeter. So by similarity, the ratio of AD over DE will have to equal the ratio of AB over BC. And if I draw those 2 triangles again separately, they'll become more obvious. And because we know AD is equal to 1 and AB is equal to 4 and BC is equal to 2, then AD over DE equals AB over BC is the same as saying 1 divided by DE is equal to 4 over 2. Or flipping to the reciprocals, DE is equal to 2 over 4. And cancelling out the 2's, that means DE is equal to 1/2. Alright, I hope that was clear. We found the similarities first, and then using the similarity, we're able to reason what other measurements were on this triangle. Alright, so pause the video now and start to work on questions 5 in the new book and question 7 in the old book. And then I'll see you in the summary, and there'll be some challenges at the end. Alright, so to be successful in this lesson, you will know the 4 tests for similarity of triangles, understand that 2 corresponding pairs of sides must be known to identify a common ratio, know how to prove that 2 triangles are similar by using the tests, and finally, be able to use similarity of triangles to find unknown values. So make sure you're confident with each of those points. And if you're not interested in challenges, well, I'm guessing you're going to leave us now, so goodbye. But for you brave soldiers who want to continue on with the challenges, hurrah, hurrah, they've finally returned. So we have two challenges today, and number one is how far did the chicken cross the road? So let's imagine a chicken who's going to cross the road. Now before crossing the road, she would like to figure out how far it is to cross this road. So let's draw this road. So the chicken first lines up a post on the other side. We'll call that P for post. So the chicken first lines up a post on the other side, and we'll mark that in as P. Then the chicken collects 4 rocks and places one, which I'll mark as A, and then moves 7 meters down the road and marks in another one, which we'll call B. And I better write this down for those who read it later. The chicken walks directly back from the road and marks in a rock, which we'll call C. And I write that down for whoever's reading it later. The chicken then measures the distance between A and C, and it's 5 meters. Then next we'll draw an imaginary line that goes from P to B and continues on. Because the chicken then walks parallel, and it's important to remember parallel, the chicken walks until it meets this imaginary line. And let's mark in that they're parallel. And finally, the chicken puts down rock D there. The chicken then measures a distance from C to D as 10 meters. And I better write down the chickens walked parallel to mark in D. So just using what we know about similar triangles, Mrs. Chicken should be able to know the distance across the road. So my question to you is, how far did the chicken cross the road? From A to P. So this might seem like a funny little example and a funny little challenge, but this is actually how we can measure distances that are a long way away. So for example, how high is a mountain, and even how far away is the moon? All right, let's move on to challenge 2, where we're going to ask you if you can prove the rule SAS. So imagine if we have a triangle, A, B, and C, and the distance from A to B is some value Y, and the distance from A to C is some value X. And in between them, we have a value alpha. And we'll call this line from B to C Z. Lowercase letters are to represent distance. So my challenge to you is to use geometric reasoning, or what we learned in linear graphs, to show if I have 2 lines joined with the angle alpha. And I'll mark that in with points D, E, and F. And the distance from D to E is equal to A times Y. And the distance from D to F is A times X. So in other words, D to E equals A times A to C. And D to F equals A times A to C. So I'll give you a hint. The way you're going to prove this is that the distance from E to F is equal to A times C to B. So my hints to you are geometric reasoning would be using parallel lines. And if you're going to use techniques from linear graphs, make D and A equal to the point 0, 0, and make B equal to x1, y1, and C equal to x2, y2. Then you might want to think about, what does that make E and F? What are the distance functions and stuff like that? All right, good luck with that challenge. I'll be super impressed if you can do that. And even if you get halfway through it, I'd like to help you get to the end. Okay, so even trying that, I'm really impressed. All right, good luck everybody. See you in the next video or in class. Bye.